Hello and welcome. In this video we are dealing with reacting mass calculations, and this is a topic that does cause a little bit of stress for students. It's part of the higher tier for chemistry GCSE, but hopefully once you go through the steps and have a go at a couple of questions, you should be a little bit more confident when you are faced with these problems. Now, first thing is I've got a reaction here. This is a word equation for a reaction. It's the reaction between nitrogen and hydrogen. On this side I have the reactants, an important keyword, and on this side I have the products, and in this case it's just one product. But ammonia in this case is a very useful substance, and because it's so useful it's very valuable. So you can imagine then that when you're making ammonia you want to make sure you have the right amount of your reactants, you don't waste any, or you don't have any unused in the reaction, otherwise it just wouldn't be profitable, or as profitable as it could be. So this is the reaction that goes on, but this doesn't tell us enough. A formula equation tells us a bit more. But the problem with this formula equation is that while we've got nitrogen and hydrogen reacting to make ammonia, we've got a slight imbalance in the number of atoms. I've got 3 hydrogen on this side and 2 on this side, and unfortunately you can't have that in chemistry. You can't magic up atoms, or you can't make them disappear into thin air. So what we have to do is to balance this, and what we can do is just put a 3 there and a 2 there. And if you're not quite sure what I did there or how that worked, there is a video on balancing formula equations that you can look at. It is an important topic and you do need to be able to do it for this course. But for now, the important thing is to be able to do reacting mass calculations, so I've balanced it for you. So here we have a balanced formula equation, and that tells us number of molecules and atoms on each side, and they all balance out, and therefore we've got these numbers here. Now this is the important part, because what we're looking at here, these numbers, I could in theory put a 1 there, so I've got a 1 to 3 to 2. These actually tell us the ratio of the different substances that are in this equation. If I know the ratios, a 1 to 3 to 2, I can work out the amounts of the different substances. Okay, now the best way to illustrate that really would be to have a go at a couple of questions. So I've got 3 questions for you to do. We'll perhaps go through the first 2 together, and you can try the last one for yourself. So bearing in mind we're working with ratios, how are we going to make ratios out of what we've got in this question here? Well, let's have a look at the question. It says calculate the maximum mass of methanol that could be made from 14 grams of carbon monoxide. So our methanol is here, our carbon monoxide is over here, and we want to know 14 grams of carbon monoxide. How many grams of methanol will that make? Well, the first step is to work with our relative formula masses. So if we take our relative formula mass for carbon monoxide and methanol, we can see that on this side we've got 28, and that equates to a relative formula mass for the methanol of 32. Now these have been given to me in the exam, or in this question, which is fortunate. Sometimes they don't give it, and you have to be able to work out these for yourself. Now, as far as this question goes, we've got 28 goes to 32, and there's various ways you can do this depending on how your maths is. You can say, well, what have I multiplied the 28 by to give me 32? And is that actual fact the answer something like 1.14 something, and whatever you did to the 28 you can do to the 14. So you can multiply the 14 by the 1.14 something, and you'll get the answer. But if you look, in actual fact, if we're working with it like a ratio, 28 to 14 have actually halved that. So whatever I did to the 28 I can do to the 32, and that gives me 16. So that's 16 grams of our methanol that's produced from 14 grams of carbon monoxide. So that's a reasonably straightforward one, and you would get 2 marks for doing that in the exam. Let's have a look at one that's slightly less simple. I've got a mixture of chemicals, contains sodium azide, which is this, which decomposes on heating to form sodium and nitrogen. Here's our balanced formula equation which we need. Again, this is a question adapted from a past paper. It says calculate the mass of nitrogen that would be produced when 130 grams of sodium azide decomposes. So we've got 130 grams of sodium azide over this side, and we want to know how much nitrogen is going to be produced. Again, we've got to work with our relative formula masses, which is our MR, but unfortunately in this question they haven't given you the MRs, they've given you the relative atomic masses, and the way we work those out is as follows. So we've got 2 NaN3. So the way we work out the relative formula mass is we say, right, Na is 23, we have 3 N's, N has a AR of 14, so we have 14 plus 14 plus 14, and that gives us an answer of 65. But don't forget this next bit here. While we've worked it out for the NaN3, you've got to remember there are 2 NaN3. So if we were to look at a pictorial version of that, or a picture of that, this is what it actually looks like. So the relative formula mass for this is 65, but remember there's 2 of them, so we just have to multiply that by 2, and that gives us 130. Okay, so the relative formula mass for sodium azide is 130, and that gives us for nitrogen, well, let's work out the relative formula mass for nitrogen. We've got 3 N2s, so for the nitrogen, N is 14, N2, so we've got 2 14s, and again it's times 3, so that's 28, but we've got 3 of those, we have to multiply by 3, and that gives us 84. So 130, this is the MR row, 130 equates to 84, and they have been a little bit kind in the exam. They've said 130 grams. How many grams does it relate to? Well, our MR is exactly the same as the number of grams, so that goes from 130 to 84. So there's no fancy calculations to do after this. 130 grams will give us 84 grams of nitrogen. Okay, so that's how we do that one there. Slightly more involved because we had to work out relative formula masses, so that was worth 3 marks. Now the next one, I think it's worth you having a go by yourself. This is again adapted from a past paper question, and quite nicely it gives us relative formula masses already. It gives us the balanced formula equation, and it's asking us to work out the mass of ammonia needed to make 6,000 grams of urea. So why don't you take a moment, have a look at this, give it a go, and I'll go through it with you to see if you can get the full marks for this question. So we want to know the mass of ammonia required to make 600 grams of urea. So first stage we deal with our relative formula masses. So here is our ammonia, here is our urea. For ammonia, which is NH3, the relative formula mass is 17, but remember there's 2 of those, so 17 times 2 equals 34, and therefore 34 relates to, for urea it's 60, so 34 goes to 60. There's no number in front of it, so we can just leave that as it is. And we want to know, in terms of our grams, we've got 6,000 grams of urea, so 6,000 grams. What's the mass of ammonia that I used? Well, again, depending on your maths, but if you look from 60 to 6,000, you have to multiply by 100, so I can very simply multiply the 34 by 100 to give 3,400. Okay, so the answer is 3,400 grams of ammonia. So that's the answer for the question. That would have got you 3 marks, and that's about it.